Hello everyone, this is Lars Olson presenting my final project on optimal blackjack strategies with DQN reinforcement learning. My problem statement is to learn expected values of various blackjack moves using a deep Q network with Keras and the OpenAI Gym blackjack environment. I also wanted to extend the basic environment that is installed for blackjack with Gym to account for a more complex version of the game. So instead of only allowing stand or hit, I also added two more possible options, those being doubling down and surrendering. Note that the blackjack environment still did not allow splitting, any sort of card counting, and it also assumed an infinite deck. So I used Python 3.6 with Anaconda, Keras 2.1.4, and ran it on my MacBook Pro. The installation steps, if you want to reproduce my code, are to first install Anaconda, run pip install gym, and then you basically have to swap out the blackjack.py file that comes with gym with the blackjack_lars.py file that is in the zip file that I provide with this project. I'd like to start out first reviewing a little bit of the code for the DQN agent. So this is a class that I downloaded from this GitHub repository, and it was initially designed for the cart pull gym problem. So you'll see a few things. First, as this is initialized, we've got all the parameters that are associated with a DQN problem. So we're specifying the observation space, so what you're seeing on the blackjack board, the action space, so all of the potential actions that an agent can take, and then some of the parameters for the actual learning model. So the discount rate, discounting future expected reward, and then of course the epsilon values that allow the agent to explore the possible actions with some sort of randomness, so it tries out lots of different strategies as it learns the game. Over here I've included the model configuration, so we're using a Keras model with two hidden layers, ReLU activations, and then the output is this linear activation that is going to essentially predict the expected value of each action, each possible blackjack action that you can make given the state of the board at that time. I also want to point out replay within the DQN agent, which essentially samples a mini batch from the memory that we're storing of previous hands and how they were played, and trains the model so that the expected value of playing a hand a certain way converges to what the actual predicted value is. So the next bit of code that I'd like to quickly review is the modified blackjack gym environment. So this is the code that is used to actually initialize the environment and play the basically play blackjack on the machine. So we've got a discrete four-dimensional action space. There are four potential actions: to stand, hit, double down, or surrender. And then we've also got the observation space, which will tell you the sum of the player's hand, the dealer card, whether or not the player holds a usable ace, and the number of moves that have been played in the hand already. So this observation space is what is passed to the agent to make a decision on how to continue on with the hand. And the action space is basically what its possible output is, its possible decision is. So I wanted to also call out, this is the code for just one function here, it's step. And this step basically defines how the agent may act. So on the left, we've got the standard actions that came with the gym environment, being a hit or a stick. And then on the right is the code that I added, which allows for doubling down and surrendering. So basically, we've extended the possible action space from 2 to 4, and we're now able to consider a more complex version of the game. So let's take a look at some of the demonstration. Okay, so the first thing we'll do with the IPython notebook is just run the first cell, which is basically going to import some packages and create the DQN agent. So that'll run for a second. So you see that Keras is running on top of TensorFlow. The next thing that we'll do once that's all loaded is create the gym environment. So this is the environment that's going to allow us to actually play Blackjack. So I'm building that environment right here. And next, we can actually kick off the training. So this code in the third cell will produce some of the outputs as the hands go on. We've got the epoch, the hand count within that, the observation data, the action taken, and the actual payout of the hand. So basically, the agent is trying out a bunch of strategies here, playing hand by hand, learning how to play the game. So once our agent has been trained, and in this case we've gone through 10,000 epochs of 20 hands each, we can start to see how the model performed. So what I've done here is plot the profits during training. So you can see early on, as the agent basically has to learn the strategy, we've got a much steeper downward sloping curve compared to around, looks like about 40,000 hands. It becomes flatter. Now it doesn't ever go up. It's never able to be profitable based on the actual environment that we've got here. But it flattens out some, and the rate of losing money slows down quite a bit. So with this model now, we can actually try to play some hands. So what I'm going to do is just play 100 random hands here. See how the agent performs. So in this case, it lost about 1250, it looks like, over those 100 hands. In this case, it won 1250. Try it again. In this case, it looks like it finished about even after 100 hands. So you see that the agent is at least over 100 hand increments playing some pretty decent blackjack. It's not losing a ton of money. It seems to have a strategy that's working pretty well. The next thing that I do is consider the possible permutations of what the player is dealt and what the dealer is showing, so that we can create a little blackjack cheat sheet, which is something that's probably familiar to any blackjack players out there. Okay, so what I'm showing here is the cheat sheet that we've learned on the left compared to one of the blackjack cheat sheets that you can find online on the right. And if you look at the color schemes, you'll see that the strategy learned by our deep QNet is actually very similar to what was learned, or excuse me, what was recommended by the cheat sheet that's available online according to the optimal blackjack rules. So, just like to point out a few things here. You'll see that it learns a lot of the double down strategy when you've got a 10 or 11 and the dealer's showing anything between a 4 and a 10. You'll see that it learns to stand when you're holding some high ace and a high card. There are some discrepancies. You'll see that the matrix on the right suggests that the dealer, or suggests that the player would want to double down with ace 4 compared to the dealer showing 5, whereas our model suggests just hitting. But overall, the network seems to have learned some rules for playing that are very consistent with what the actual optimal rules for blackjack are based on this decision matrix here. There are also, with these blackjack charts, usually some more rows that define what happens if you're dealt 2 cards of the same hand and are able to split, but I did not include those here since that wasn't part of the game. So let's actually explore some of these discrepancies. I think this is kind of interesting. So we can look at a case first where we're holding an 11, a sum of 11 in our hand, and the dealer's showing an ace. So the online cheat sheet suggested that we double down. But the cheat sheet that our model learned suggests hitting. So let's actually plug the this input into our model to see how it's thinking about the payout and how it's arriving at the conclusion that it should just hit. So the output of this scenario is that, well, standing's a bad idea because you're expected to lose half a buck. Hitting, you're expected to make 9 cents on the dollar. Doubling down, you're expected to basically break even, and surrendering, you're supposed to lose 50 cents on the dollar. So you'll see that hitting and surrendering here are actually very close in terms of expected value. So the difference in doing either is relatively minimal based on that hand. Another discrepancy between the learned cheat sheet and the online one is when the player is holding a sum of 16 and the dealer is showing a 10. So the online cheat sheet suggests surrendering, whereas our model prefers hitting. So let's see how our model is thinking about the payout. So when you run the guess payout function here, you'll see the various payouts for each of the possible actions. And in this case, again, hitting, you're expected to lose about 44 cents on the dollar, whereas surrendering, you're going to lose 50 cents on the dollar. So it's another case where the discrepancies between our model and the online supposedly optimal blackjack matrix, they disagree, but they're still suggesting a pretty similar approach to the game. So some quick conclusions here. First, I'd like to say that the model did a pretty good job of learning blackjack, even some of the advanced strategies such as doubling down and when that's advantageous. I'd like to point out that this gym environment the gym environments that we download can be extended. You can play with them and you can kind of make them your own. And personally, I would like to at some point add in the splitting functionality and card counting into this code base to see whether or not our agent can actually turn a profit if it employs those two strategies as well. And then I'd also like to point out that there's open source code out there that you can download that will allow you to basically implement a DQN agent with relative ease, and you can apply that to different types of games than just what I've shown here: blackjack, cart pull, and many more. Thank you for watching.